let's start with what the structure of an atom actually is.
Yeah.
That's going to be helpful to understand what we even mean by neutron here. So an atom and how it is possible for everything to be made of atoms, but also be different things, is what's called the structure of the nucleus. So an atom is three main components. There is neutrons, there are protons, and then there are electrons. Those are the three things that make up an atom. The neutrons and the protons are really heavy particles. They clump up in the middle of the atom called the nucleus. And those two particles are surrounded by what's called electrons in orbital. And the important part to nuclear energy are specifically the neutrons of the nucleus. Those are the main part. But when we see something like californium-252, whatever the frick that is, and plutonium-238, these numbers 252 and 238, that's the number of neutrons. So if you see
is it the number of neutrons or the number of neutrons and protons? Combined.
It might be them combined.
I think it
might be them combined. Yeah. So there's the atomic number. If you see a element on a periodic table, there's usually in the top right-hand side of its like little element square in the periodic table, that number is the amount of protons in the nucleus. The amount of protons in the nucleus make up what type of atom it is. Like, if we are to, like a hydrogen atom, its atomic number is 2.
Right.
Because it has 2 protons. But it also has 2 neutrons. That makes up the nucleus of a hydrogen atom. And then there's electrons around it in orbitals. But yeah, that's what we are talking about with this whole neutron business. And the reason it's called nuclear energy is because we are dipping our hands and stirring the nucleus of the atom.
So the fuel that we're going to use, in the reactors that are relevant to today, there are different types of reactors that use different types of fuel. But we're going to be using a heavy nucleus like uranium-235. When uranium-235 absorbs a neutron, it briefly becomes an excited nucleus called uranium-236.
Excited meaning in a state of high energy and instability.
Yes.
So atoms are always looking to be in a lower energy state, and lower energy states are more stable, roughly speaking. So but one thing that makes them stable is an even balance between the protons and the neutrons. So protons are positively charged, neutrons are negatively charged, and neutrons are neutral charge. It's literally in the name. They have no charge. Electrons are negatively charged. So for there to be an even this is the same thing. This is electromagnetism, right? This is the same thing as a magnet. You have 2 positively charged magnets. They want to run away from each other. If you have a positive negative charge magnet, they suck, right? They stick to each other. It's no different at the subatomic level. So if you have an uneven amount of these different charged particles, things are going to get wonky. Some are going to get blasted off. There's another thing called the strong nuclear force, which is what holds the nucleus together, that can overpower electromagnetism. But roughly speaking, when something is excited, it is in a high energy, unbalanced state, and it wants to blow off some of its particles.
Which is exactly what happened. So in the case of uranium-236, it splits into smaller fragments, and these are going to be called fission products. So again, that makes sense, the products of fission. There are 2 main atomic masses that will generally be split into. I think it's, 135 is one atomic number that generally these fission fragments are going to split into, and I don't remember the other one. I think it's like 50-something or 60-something. So what happens is when it absorbs a neutron and it splits, it is more likely to split into nuclei of these atomic numbers, if that makes sense. So I mentioned one side of that fission product yield graph is going to be around 135. So that means one common fission product is going to be xenon 135 with an atomic mass of 135. And we're going to talk a little bit about that later because that is very important for reactors. But before we get there, right after fission, so we got your fission products. Right after that happens, you also have what's called prompt neutrons. Prompt neutrons kind of fly out of the this whole thing that just happened here. This whole, not explosion, but this.
I mean, it on a subatomic level, it kind of is.
You have prompt neutrons, and now there's generally going to be 2 to 3 of these. I think the average is like 2.4. Generally average. So 2 to 3 neutrons are going to fly out of the whole deal there. And what they're trying to do, not trying to do anything, but what they're going to do is they're going to interact with more uranium-235 and to repeat this process over and over again. That is what's called a chain reaction. If the amount of fission events that are occurring supply enough neutrons to further create more efficient events with more reactor fuel, you have what's called a chain reaction.
So, yeah, the way you might wonder, like, okay, what does this have to do with creating energy? And so this stems back to one of my favorite people in history, Albert Einstein.
Smart dude.
So when a neutron enters the nucleus of a uranium-235 atom, causing it to be unstable, an unstable isotope that is uranium-236, causing it to blast apart. And by the way, this happens in much shorter amount of time than humans could ever perceive. Like it's fractions on fractions on fractions of a second. So when that happens, you don't get a perfect even amount of however many protons, neutrons, and electrons were in the uranium-235 atom, just split apart. It's not a perfect conversion. Mm-hmm. So some of those particles disappear. And you might ask, well, where the frick did they go? Right? That they got converted into energy. So that's where Einstein's E equals MC squared comes into play, is energy is equal to mass times the speed of light squared. Mass and energy are interchangeable, right? We can't convert energy into mass, but, well, can we? I don't actually know if that's true or not, but we definitely can convert mass into energy. So some of these particles, quote unquote, disappear. They don't actually disappear. They just get converted into energy. That energy is what we use for our energy production. So the reaction of mass, the loss of mass when splitting the uranium atom, gets converted into energy. And that's why, which generates more neutrons, which hit more uranium-235 atoms, which causes more to split, losing mass, creating more energy, and so forth. That's how energy is actually created, is because we are literally turning mass, turning weight into energy.
Right, and then energy also, you could say, heat.
Right, which is to say heat, yeah, same thing.
Which will matter later, and we're going to go over that. So we have defined what is happening more or less in fission, and then how fission can result in a chain reaction of more fissions, should you have enough fuel in a close enough range so that the neutrons can fission with them. Mm-hmm. Now, let's define some terms here, because this first one is actually a really important term. So you'll hear people talk about nuclear energy, and kind of in like the Hollywood sense, and they'll say, "Oh, it's going critical."
Going critical.
It's going critical.
That usually means a bad thing.
It usually means a bad thing. Well, it doesn't. It doesn't actually mean a bad thing. So essentially, all criticality is just what I said. If you have enough neutrons, prompt neutrons coming out of the fission event that are enough to supply neutrons for a further fission event, you are critical. And if that ratio is kind of stable, and you don't have too many neutrons or not enough neutrons, you are critical. Then supercritical would be you have too many neutrons, and then subcritical you'd have not enough.
When I think of critical, I think of like a Hollywood movie in the world of like a power plant. When I see critical, I think of critical red flashing, blinking on a screen. Something's about to blow the frick up.
Yeah, which is
this is not that critical.
The irony is that you'll have those blinking red lights with anything other than criticality.
Right. Yeah.
Right.
Yeah.
Criticality is kind of what you're after.
That's what you want. You don't want, more or less, but overcritical, supercritical, or subcritical. But yeah, that's. I don't know if we might talk about this later, but that's actually the biggest problem with fission reactors is you can't easily just turn them off. There's not an off button for a fission reaction. Mm-hmm. So,
well, kind of is, as far as like,
there's scramming, which we might.
We will talk about that. That's kind of what I was going for. That's about as good as you can get, I would imagine.
Right.
As far as stopping reactions or the ability to react. To kind of complicate the system further, we're talking about neutrons being captured by uranium-235 to start the fission process. Mm-hmm. Now, in specifically the types of reactors that we're talking about today, you can't have fast neutrons. So a fast neutron is going to be a neutron traveling at around 14,000 kilometers per second. Which is
you can't outrun that one.
Which is really dang. What was that thing? You told me something. You told me a fun factoid about distances.
Well, 14,000 kilometers is a very significant portion of the United States.
Yeah, in a second.
But in a second.
Yeah,
in a second. Yes, that's insane. Imagine going like freaking halfway across the United States in a second. Mm. This is how fast. Now, this is crazy. So neutrons are quick, but like subatomic particles can move fast. And the thing about neutrons is because they are of neutral charge, they are not attracted or repulsed by other atoms. They can shoot right through stuff and just go blast through unharmed, right? Yeah. They're probably going to smash into an atom nucleus, eventually, because there's a lot of them. But if you also know, atoms are largely empty space. The nucleus is extremely tiny. So the nucleus to the electrons that are in orbitals around it is so if a nucleus was the size of the Earth, the electrons would roughly be about as far away as the sun. That's how much space there is between the nucleus of an atom and the electrons around it.
Yeah.
That's insane. That's what people mean by atoms are mostly empty space. Yeah. So if a neutron is flying past the United States at 14,000 kilometers a second, it is easy for that thing to just fly through walls and what you would think as the most hard structures imaginable. It's because these structures at the subatomic level are literally universes between them. So that's why something like a subatomic particle can just fly through anything so easily, is because there's not really much for it to hit. Eventually it will smash into a nucleus, right? But what's fascinating is even this fast neutron is just a pathetic fraction of the speed of light.
Right. Yeah. So those are fast neutrons, and that's a really interesting thing you just told me there. That's crazy. Yeah. But as far as uranium-235 is concerned, it wants nothing to do with that fast neutron. It's not going to be able to absorb that. So you got to slow these suckers down to they call these thermal neutrons. So that's going to be about 2.2 kilometers per second.
That's nice and slow. That's nice and slow. That's 2 kilometers per second.
That's pretty dang fast, but that's a lot more manageable, I would say. And
much greater chance that it's going to get captured by a uranium nucleus at that speed.
Right. So the natural next question is, how do we slow these suckers down?
Yeah.
Right,
Because as I just said, they can travel through almost anything at that speed.
So how do we slow these suckers down? If we are operating a nuclear reactor, we want fission to occur so we can have power output. So we got to slow these suckers down. So how are we going to do that? And to do that, let's talk about the reactor core. And specifically, we're going to look at a pressurized water reactor.